On our previous discussions, we've introduced the general approach in the analysis of resistive networks. I've discussed Kirchhoff's voltage law and Kirchhoff's current law, and together with Ohm's law, we could practically determine voltage and current on any elements on a circuit. In this module, we will discuss two popular uh, techniques in the analysis of resistive circuits. These are the mesh analysis and the nodal analysis. So the mesh is more geared towards the use of Kirchhoff's voltage law, while the nodal analysis is focused more on the use of Kirchhoff's current law. In this video, we'll start first with the mesh analysis, and after that, we'll proceed with the nodal analysis. So the learning objectives for this module or for this video is to describe the steps behind the use of mesh analysis, and we'll also illustrate or give some problems to show how the mesh analysis work. So the mesh analysis or mesh technique is uh, geared towards the use of Kirchhoff's voltage law and Ohm's law. It does not use the Kirchhoff's current law. Let me show how the mesh technique works in circuit analysis by doing an example. So this example is the same example that we did on our previous videos. So here we have a two-loop network uh, containing two independent voltage source, and we're asked to determine what is the current I sub 1 and the voltage V sub 3, where it is specified what is the direction of I sub 1 and the polarity of voltage V sub 3. The first step in using the mesh technique is to identify the small loops in the network. So let's say this is our circuit, and we can see that there are two small loops. So let's label this as loop A, and this one is loop B. And the next step here is to assign a circulating current with an arbitrary direction in each of these loops. Okay, so we'll assign a loop current. So let's call this I sub A, and this one is I sub B. Okay. These loop currents are imaginary currents that go around the loop. So for example, loop current IA passes through the 5-volt element, the 2 ohm element, and the 8 ohm element. Loop current IB passes through the 8 ohm element, 4 ohm element, and the 3-volt element. So take note that there are two loop currents that passes through the 8 ohms. One is I sub A going in this direction, and the other is in this direction, which is IB. The third step is to identify the polarity of the voltage drop across each of the resistances due to the loop currents that pass through those elements. So for the 2 ohms, for example, the loop current IA is moving in this direction, so therefore the positive should be on the left side and the negative on the right side. So for 8 ohms, the polarity of the voltage drop is for I sub A. So there are two loop currents that passes through the 8 ohms. So the voltage drop due to IA is the positive should be here, the negative here, and for I sub B, the positive should be here, and the negative should be here. For the 4 ohms, so the current I sub B is moving in this direction, so the positive should be here and the negative here. We don't need to label the independent voltage source since they already have their own polarities. For the fourth step, we can now write the KVL equation for each loop where the loop current has been assigned, except for the loop that contains a current source. So since the two loops here does not contain any current source, we can now write down the KVL equations. So here are the KVL equations. So for loop A, so this is the equation for loop A, that would be minus 5. So we go around clockwise while we add the voltage drops. So that's minus 5 plus 2 I sub A plus 8 I sub A minus 8 I sub B, since there are two voltage drops across the 8 ohm element, and that would be equals to 0. For loop B, so that would be minus 3 volts. So again, we go around clockwise while adding the voltage drops. So minus 3 volts plus 8 IB, so this is 8 IB here, minus 8 IA, so here is minus 8 IA, plus 4 IB also equals to 0. Here are the two equations properly rearranged. So solving these two equations, two unknowns equations, we will arrive at I sub A equals 1.5 amperes and I sub B 1.25 amperes. Now that we have the values for the mesh current, we can now solve for the unknowns required. So for I sub 1, that would be negative I sub A, or equals to negative 1.5. So let me explain why is that so. So this is the 2 ohms, and we know that the mesh current that flows through there is I sub A in the given direction, and what we're looking for is the actual current that flows represented by I sub 1 in the given direction. Now since I sub A is flowing in the opposite direction and I sub 1, that would only mean that I sub 1 must be equals to the negative of I sub A. Take note that in getting the actual current, we're trying to get the combined effect of the mesh currents that passes through the elements. And in this case, there's only one mesh current, and that is I sub A. However, it is in the opposite direction, so therefore I sub 1 must be equals to the negative of I sub A. Now for V sub 3, to get V sub 3, we need to know what is the current, the actual current that flows through the 8 ohms. So let's assume that the current there is I sub 2 with a given direction. So we also need to express I sub 2 as the total effect of the mesh currents that pass through the 8 ohms. So since I sub B has the same direction, or I sub A has the same direction as I sub 2, this has a positive effect on I sub 2, so therefore that should be I sub A. However, since I sub B has a negative effect because it has the opposite direction, the effect is negative. So therefore, I sub 2 there should be I sub A minus I sub B. And we can proceed in solving V sub 3. So by Ohm's law, this should be minus 8I2. So minus because the polarity due to the direction of I2 is that the positive should be at the top. And since we are looking for V sub 3 with the positive below, so we have to introduce a negative sign. So V sub 3 equals minus 8I2, but we know I2 to be I sub A minus I sub B. So therefore, we will get negative 2 volts. So therefore, we have I sub 1 negative 1.5 amperes. So the negative simply means that the actual direction of the current through the 2 ohms is in this direction with a value of positive 1.5, and V sub 3 is negative 2 volts. So that means the actual uh, positive side, the actual voltage across the 8 ohms is that the positive is really on top and the negative is below the 8 ohms. It is important to note that when we wrote the KVL equations, the voltage drops across the resistances, so this is the voltage drops, can be summarized as this voltage drop, which is really the voltage drop inside this loop due to this current in this loop, loop A, which is simply just the sum of 2 and 8 times this current minus the drop due to the currents outside of this loop. Okay, so for loop B, for example, the voltage drop across the resistances is the drop due to I sub B, which is simply the sum of 8 and 4. So we have the 12 IB minus the drop due to the current outside of loop B, which is 8 IA. Now, this observation is very important when we do mesh analysis because it makes the process simpler and faster. Let's proceed with some examples to further illustrate the mesh analysis. So in this example, we have a network and we are required to solve for the current I. That is the current that passes through the 1 ohm going in the upward direction. So to solve this using mesh analysis, first we identify the loops, the small loops. So here we have loop 1, 2, and 3. And then we assign loop currents. So for loop 1, we have I sub 1 going in the clockwise direction, 2, and I sub 3. So it is important to note that when we assign loop currents, uh, it is much easier if we assign them having the same direction. So in this case, all the loop currents have the same direction, which is in the clockwise direction. So for loop 1, we can now proceed in writing the KVL equations. So for loop 1, that would be plus 8. So we start here. So that would be plus 8, and we move in the clockwise direction. So we move in this direction, something like that. So plus 8, because this is positive here. Then 4 plus 2 plus 1, that would be 7 I sub 1. So 7 I sub 1 minus any voltage drop due to the currents outside of loop 1. So that would be minus 2I2 and minus 1i3. So this is the equation. So again, it's 8 plus 8 plus 4 plus 2 plus 1, so 7i1 minus 2i2 because this drop is due to the current outside loop 1. So we need to put a minus sign and another negative voltage, so that would be minus 1i3 because I3 is outside loop 1. Then simplifying this, we will get this equation. For loop number 2, we have this equation. So starting here, moving again in the clockwise direction, same as the direction of the loop current. So minus 6, 2 plus 10, that would be 12i2, so positive 12i2, minus any drop outside of this loop 2, so that would be minus 2i1. Okay, we didn't include minus 6 or minus 6i3 because this one is not the resistance. So therefore, this is equation number 2. Then for loop 3, so we start here. So we move clockwise. So minus 8 volts. So then we jump to the 6 volts, so that would be plus 6 volts. Then 1 plus 5, that would be 6i3 minus 1i1 because that drop is outside, uh, that drop is due to I1, which is outside loop 3. So simplifying, we will get this equation. In solving for the three equations, we will get these mesh currents. And solving for I, we should get I3 minus I1. So the current through the 1 ohm is a combination of loop currents I3 and I1. So since I sub 3 has a positive effect on the current that we're looking for, which is I, but the loop current I1 has a negative effect, so therefore it should be I sub 3 minus I sub 1, so that will give us 1.188 amperes. So let's have our second example. So again, in this example, we have a dependent voltage source, and we're required to compute for the current through the 2 ohms in the downward direction. So again, we identify the loops in this network. So there are 3 small loops. So let's label the, let's assign loop currents in those loops. So we have I sub 1 here, I sub 2 here, and I sub 3 there. Next is we can write the KVL equation for loop 1. So we start here. So we go around clockwise. So in this direction, same as the direction of current I sub 1. So we have plus 5i. So remember, this one is a voltage. Then minus 10 plus 6i. So there's only one resistance inside the loop, so that would be 6i sub 1 equals 0. Now we need to express I, which is this current, in terms of the loop currents. Remember, I here is the actual current that flows through the 2 ohms, while I sub 1 is a loop current. So we need to express I as a loop current. Now we know I here, the current through the 2 ohms, there's only one loop current that flows through that, and that is I sub 2 going in the upward direction. So this one is I sub 2. So therefore, I is the negative of this. So therefore, we replace I by negative I2. And simplifying, we will get this equation. For loop number 2, so that would be um, positive 10 plus 4 plus 2, that's 6 I sub 2 minus 4 I sub 3. So that will give us this equation. And for the third loop, we will get there, so starting from here, going in the clockwise direction again, so that will be negative 5i. So here, plus 3 plus 4, 7i3, then minus 4i2 equals 0. Simplifying, we will get this equation. In this problem, the loop currents are already given. So we have loop currents I1, I2, and I3. And we're asked to solve for V sub naught. So take note that V sub naught here would be equals to 4 times the current in this direction. So that would be I sub 1 minus I sub 3. So that would be I sub 1 minus I sub 3. Okay, so let's proceed to the solution and solve for the mesh currents. Okay, so first for loop 1, this will be the equation. So that would be 1 plus 2 plus 4, 7i1 minus 2i2 minus 4i3 minus 40. We transfer 40 on the right side, we'll get positive 40. Uh, Let me skip loop 2 and proceed to loop 3. So for loop 3, we have uh, 4 plus 8, so that will be 12 I3 minus the drop 4 I1, then minus 20, so we transfer it to the right side, it becomes positive 20. So that is loop or equation number 2. Now for equation or for loop 2, uh, since we have an element that is a current source, so I've stated in the steps previously that uh, we only conduct KVL equations, we only write KVL equations if the loop contains no current source. Now this loop here contains current source, so we cannot initially write KVL equations because this one is not a resistance nor it is a voltage source, and therefore we don't know the voltage across this current source for the moment. So we cannot uh, write a decent KVL equation in this loop. But take note that because this is current source and it is 5 amperes, it already gives us the answer. What is the actual current here? The actual current here is already 5 amperes. Okay. And in terms of the loop current, the actual current here is also I sub 2. So therefore, I sub 2 must be equals to 5 amperes. So we immediately can write I sub 2 equals 5 amperes, and that should serve as our equation number 3. So solving the three equations, three unknowns, we can get this uh, mesh current. So I sub 1, I sub 3, and I sub 2 is already given. And lastly, we can now solve for the voltage V naught. So we earlier said that is equals to 4 times the quantity I sub 1 minus I sub 3. So that should give us 20 volts. In this last example, we are required to get the outflow currents I1, I2, and I3. Take note that we have two current sources. So there will be at least two loops that are affected and from which we cannot perform a KVL equation. We cannot write the KVL equation because of the presence of the current sources. So first, again, following the steps, first we assign loop currents. So we identify the loops. There are four small loops, and we assign loop currents I sub A, I sub B, I sub C, and I sub D. And then after that, we can write the KVL equations. Now for I sub A, we cannot write KVL equations because of the presence of 4 amperes. In loop D, where there is the loop current ID, we cannot also write because of the presence of the 1 ampere uh, current source. Likewise for loop I sub B. So the remaining loop where we can write a KVL equations is in this loop, since it does not contain any current source. So this loop does not contain any current source. So writing the KVL equations, that should give us this equation. So that is for loop AEDA. So minus 8 volts. So we transfer that to the right, it becomes positive. Then 12 plus 4, that is 16 I sub C, because in this loop we're dealing with the loop current I sub C minus the drops due to the external currents to this loop. So that will be minus 12 IA and minus 4 I sub D. Okay, so that is the equations. Take note that we have 4 unknowns to solve, so we need 3 more equations. Since we don't have any more small loops from which we can write KVL equations, we need to look for a larger loop called a supermesh that does not contain any current source. And once we identify that, we can now write a KVL equations. Now, loop, one super mesh that we can look up is the loop D, E, B, C, D loop. This loop does not contain any current source, and therefore we can write the KVL equations. But since this now spans two small loops, so this loop and this one, we need to write uh, the KVL equation uh, on a per element basis. So for example, that would mean that we need to add the voltage drop across 6 ohms plus 10 plus the voltage drop across the 2 ohms plus the voltage drop across the 4 ohms. So in doing that, we need to identify the polarity of the voltage drops across the resistive elements due to the loop currents. So for example, for I sub A, that would be the polarity should be, it should be plus here, minus here. So for I sub B, that will be plus here and minus here. So all in all, this will be the polarity of the um, so let me erase the ink. So that would be the polarity of all the voltage drop across the resistive elements. So using this polarity, we can now add the voltages across the elements while we go around the loop DB, DEBCD. So starting from the 6 ohms, for example, that equation would be this one. So this one is due to this drop is due to the loop current I sub A, and that would be minus 6 IA. So minus 6 IA plus 6 IB plus 6 IB. Then we proceed to 10, and that is plus 10. So we transfer that to the right, we get negative, and then plus 2ID, okay, 2ID. So that's 2ID. So let me first write it here. And then we proceed here. So there's only one loop current passing through 2 ohms. Then we proceed to the 4 ohms. We have plus 4ID plus 4ID. So that's why we have here 6ID. And then minus 4IC. So that this is the term here. So that would be the equation for this loop DEBCD. Okay, now we have two equations and we need two more. Now we can't find any more super mesh that does not contain a current source. For example, this one, we cannot use this because of this current source. We cannot also use this one. There's also a current source. So the next move here is to express the independent current source in terms of the loop currents. So for example, I sub A here must equals 4. Okay, and 1 ampere here should be the combination of loop currents I sub B and I sub D. I sub B is a positive effect while I sub D is a negative effect. So therefore, 1 should be equals to I sub B minus I sub D. And that should serve as our equation number 4. And therefore, we can solve for all of the loop currents. And that should give us, so these are the loop currents. Um, so I didn't show here the values for the loop currents, but after solving those loop currents, you can now use these equations to solve the actual currents I sub 1, I sub 2, and I sub 3. So I sub 1 here is the combination of loop currents I sub B and I sub A. So I sub B has a positive effect, so therefore it is positive IB. I sub A has an opposite effect, so therefore minus I sub A.
and also similar for the other actual currents I sub 2 and I sub 3. So that's it for this video, and on our next video we will discuss the nodal technique. So it's the this technique uses a lot of KCL, the Kirchhoff's current law, to solve network problems.